People often say that what goes up must come down. And that's sort of true for the most part as you study physics until you reach a certain point in your understanding of gravity. And for us, that point is today. We're going to have to adjust this saying a little bit to what goes up must come down unless we throw it really, really hard. And so this is basically introducing the idea of what we call escape velocity. And the thought is this: if you throw an object directly away from Earth or from any other planet, escape velocity is the velocity you need to give it so that it never falls back down or never comes back. Now, if I want to throw something up and have it never come back, it needs to never stop. If it were to stop, then we'd have a force of gravity acting on it, and that force of gravity would start to accelerate it back towards Earth, and then it would just be a matter of time until it came back. So I have to throw it hard enough that it never stops. However, because as it moves further and further away from Earth, gravity is still acting on it, it will still be slowing down. So it can never stop, even though it will always be slowing down. Now, that can seem like a bit of a contradiction at first. If I always slow something down, won't it eventually come to a stop? And to sort of illustrate how something like this might be possible, we can think of it sort of like, what's the word in mathematics? A geometric series. If that word doesn't mean anything to you, that's fine. But imagine something has a velocity of 10 meters per second. And then a little while later, it has a velocity of half that, 5 meters per second. And then a little while later, we cut the velocity in half again to 2.5 meters per second. And then a little while later, we cut it in half again and again and again and again. And I can keep doing that process forever, always cutting the velocity in half. And that means my object will always be slowing down. But I can't make something zero by cutting in half. So my velocity would never actually stop. Now, that's not necessarily the exact pattern that an object trying to escape Earth's gravitational field follows, but it demonstrates how this idea of never stopping, even though you're always slowing down, is possible. Now, it turns out if I try to set up this exact scenario and I launch something away from Earth and have it continue to move higher and higher and higher, further and further away, always slowing down, but I make sure it goes fast enough that it never actually stops and never comes back. What happens is it'll need to eventually make it to infinity. It'll eventually, if I give it enough time, make it infinitely far away from Earth. This is important because that means it'll eventually have a potential energy of 0. Recall we've been saying lately that for our new formula for potential energy is 0 for things that are infinitely far away. Now, something that I haven't maybe explicitly said about this scenario, although perhaps you've sort of inferred it, is that this idea of escape velocity, we usually apply it to things that are being thrown in that they don't have a rocket or something on them that's continually providing thrust. They're given an initial speed right at the beginning, and then they just become a projectile after that. If I want something to go up and never come back, and I have a rocket attached to it, there are other ways I can achieve this. I don't need to end up infinitely far away. If I have a rocket on board, I can always give myself a boost if I start to fall back down towards Earth. So the idea of escape velocity applies specifically to things that don't have thrust, that are given an initial velocity, and from that moment onwards, they are just projectiles. They feel only the force of gravity and nothing else. So back to this idea here. If the idea is that this thing is going to eventually make it to infinity, where it will have a potential energy of 0, what that means is we need to give it enough kinetic energy to completely cancel out its potential energy. Right? It'll have some potential energy at the beginning, but that has to end up going to 0 as it gets infinitely far away. And how do I make that potential energy go to 0? How do I get it to go infinitely far away? By giving it a ton of speed, by giving it a ton of kinetic energy. So this concept really boils down to a balance between kinetic energy and potential energy. I have potential energy. I want it to go away. I want it to go to 0. And how am I going to do that? By giving it a certain amount of kinetic energy. So let's see how this sort of works out with a problem. At what speed do you need to throw a 1 kilogram rock in order for it to leave the Earth's gravitational pull? And by that I mean never come back. This question is effectively asking, what's the escape velocity for a 1 kilogram rock if we launch it from Earth's surface? So the way we solve escape velocity problems boils down to using the law of conservation of energy. So let's start with that. Okay, so now let's go through our usual step of figuring out if there's anything in this formula that is 0. So at the beginning, I have a rock. It's sort of on the surface of the Earth, and I've given it some speed. I've given it a huge amount of speed. I've thrown it, and it hasn't yet made it up, through the atmosphere into space, but it's got that initial speed, and now I'm just waiting as it's going to go higher and higher and higher. So it has some potential energy initial. Even though we're at Earth's surface, that's not where potential energy is 0 anymore. So I do have some PE initial. And I've thrown it. I've given it some kinetic energy initial. And now I'm going to wait to see how those sort of evolve over time. So as this rock goes higher and higher and higher and higher, the only force acting on it is gravity. So the only thing that could possibly do any work on it is gravity. Since there are no other forces that could do work. So this work term is going to be 0. Gravity will do work on it, but other things won't. Now, final is going to be that the end of this rock's journey, where it ends up at infinity. Which means my potential energy final will be 0, because R is going to be equal to infinity at the end of this rock's journey. And my kinetic energy final, well, if my rock makes it to infinity, if it makes it so far away that it can't even feel Earth's pull anymore, and it still has a ton of speed, then that means I probably threw it harder than I needed to. So yeah, I can give this thing extra speed and it'll make it there, but I just want to know how much speed I need in order to get there. There's a certain amount of speed I'll need to make it to infinity, and if I have extra speed on top of that, then I'll have extra speed when I get there. But because we just want the speed we need, we're going to say we have no extra speed once we get there. Our kinetic energy final is 0. When I get to infinity, I want to have no energy at all, no potential, and no kinetic. So this means the formula kind of gets rearranged to look a little odd. I've got potential energy and kinetic energy at the beginning, and I've got no kinetic energy at the end. Now, what I'll maybe do to make it easier to solve for the speed, which is related to the kinetic energy, I'll sort of isolate the kinetic energy here. So I've got kinetic energy initial equals negative potential energy final. I've just moved this term to the other side of the formula. And now let's plug in some formulas. So kinetic energy is 1/2 mv squared. And potential energy is negative m1 m2 big G over R. This is kind of nice here because I have these two negatives that I can basically cancel out. One is the negative that's in the potential energy formula, and one is the negative I got from moving potential energy to the other side. And so now I think I'm at a place where I can, in one step, isolate V, this guy right here, and find the speed I need my rock to have at the beginning so that it makes it to infinity. So let's rearrange this formula to isolate V. This M over here is going to come down to the other side. And to get rid of this 1/2, I'm going to basically multiply both sides by 2. And then to get rid of this squared, I'm square rooting both sides. Now there is an opportunity to maybe cancel out some m's here. I've got 2 m's up on the top and 1 on the bottom. Which one is that that's on the bottom? Is that an M1 or an M2? Well, let's have a look. This M1 and M2 I have over here. One of these is going to be the Earth, and one of these will be the rock. The convention I like to use is M1 is the smaller object, M2 is the bigger object. So let's label that in here. So M1 is the rock, M2 is the Earth. And so what about the M on the other side? What about this M over here? Well, this was the kinetic energy formula. So this is the object that has the kinetic energy. That's the rock. The rock is the thing I'm throwing, not the Earth. So that M is the rock. So I can see which M is actually the same on both sides. It's M1, the rock, is on both sides. So when I'm canceling out some M's here, it's going to be this M and this M that cancels out, leaving me just the mass of the Earth. So this brings me to a formula for escape velocity. And notice, we haven't actually plugged in any numbers yet. So everything I've done so far would be the same, regardless of whether I'm talking about a rock or a spaceship or a piece of dust or a tennis ball, and regardless of whether I'm talking about the Earth or the moon or Jupiter or Mars or the sun. Everything we've done so far basically just says we've got an object and we want to give it enough velocity that it never comes back. So we've actually derived a formula for escape velocity, which is that escape velocity is the square root of 2 times the mass of the object you're trying to escape from times big G over R. So this is almost worth putting a little box around. In some courses, you might actually have this as a formula on your formula sheet. It's the formula for escape velocity. But I feel like that's not necessary because we were able to derive it pretty simply. And I would rather than have you memorize this formula and not really know what it means or where it came from, I would rather you be able to take this formula and say, okay, if I want to throw something so hard that it never comes back, then I need it to end up with a potential energy of 0, and I don't want it to have any extra kinetic energy at the end. And if I want to not push on it while it's moving away, work other is going to be 0. And if we do that, and then just do a little bit of math, we can basically recreate this formula whenever we need it. So how about this particular question? What is this formula going to give us? Well, let's see. M is the mass of the object we're trying to escape from. In this question, that's Earth. So this is 5.97 times 10 to the 24 kilograms. Big G, I won't bother writing it out. And R is how far you are away from the planet's center when you start, right? That R was over here. That's where we first saw it. That was the potential energy. Oh, and my apologies, we've got a mistake here. This says potential energy final. This should say potential energy initial because it came from this side and we just moved it over. So this R is from the potential energy initial term. So it's how far you are from Earth's center when you're launched, when you're thrown. So in that case here, since we're launching it from the surface of the Earth, that's going to be the radius of Earth. So 6.38 times 10 to the 6 meters. And if I plug that all in, I get 11,200 meters per second. If I throw a 1 kilogram rock straight up in the air at that speed, it will never come back. Now, the reason you may not have heard about this idea before, and the reason we tend to say whatever goes up must come down, is because actually doing this is really hard. To put this in perspective, that's a little over 30 times the speed of sound. To make matters harder, we have actually assumed here that there are no other forces doing work on this object as it goes up. But because Earth has an atmosphere, if I actually threw something at this speed, there would be a tremendous amount of air resistance acting on it right from the beginning. And that atmosphere would do actually a ton of work on it. So this idea of escape velocity is sort of more useful in situations where we're maybe starting from an object that doesn't have an atmosphere, like if I want to launch something up from the moon, or if I'm starting at a height where I'm already above the atmosphere. Like perhaps I'm already in orbit around the Earth, and I'm above the Earth's atmosphere, and now I want to make it out to infinity. And we kind of noticed, let's look at this next question here. Does the mass of the rock matter? Well, no. And you might remember as we went through this, we canceled out, this was the mass of the rock there and there, right, from these 2 points. And they canceled out. So we saw that mathematically. Let's just think about what that means. It means that if I want to throw something up and never have it come down, and I'm assuming Earth air resistance is negligible, it doesn't matter whether I'm throwing a rock or a school bus or a building or a space station. If I want it to go up and never come back down, this is the magic number I have to throw it at. You might think that heavier things would be more likely to fall back down. Something that's heavier, you're going to have to give it a lot more speed. Turns out that's not the case. Escape velocity is completely independent of the object you're throwing. All it depends on is the mass of the object you're trying to escape from and how far you are from its center when you start, the place you get thrown from. So to answer this question, does the mass of the rock matter? No. That M canceled out. All objects have the exact same escape velocity, assuming they're trying to escape from the same planet. Escape velocity doesn't depend on the mass of the object being thrown. So there you go. Hopefully that gives you enough info and enough practice to start solving some problems to do with escape velocity. And remember, my preference is that rather than remembering this formula or writing it down and using it every time, you remember the concepts we use to get there. And you just start with this formula every single time. And then it's just a couple of lines of math to get to here. And I left all the numbers out until sort of the very end, but you can feel free to plug numbers in much sooner. We could have started plugging numbers in at this step if we wanted to, and you're very welcome to do that.